All right. Hi, everyone. Thanks for coming. You're here because you want to hear about CMake, right? This is the room about CMake. Just checking. All right. Getting started. This is pragmatic CMake, as told by Bret Brown. I am Bret Brown. I am from Bloomberg, where I work full-time in developer experience. And I'm here to help you with your CMake headaches. We all have them. I probably have more than you because I probably write a lot more CMake than you do. It's got a lot going on, doesn't it? There's like a lot of stuff, a lot of docs, a lot of APIs. Sometimes different APIs do the same thing and you're like, which one do I use? It has actually decent, pretty good. Actually, I actually like the reference docs. They're very thorough in my experience, but you really need some good parts, right? What are the good parts? Like, what's the step-by-step? How do I get into that? Like, how do I hold that tool, right? So this is my attempt at helping clarify things, refresh things, update things for you, perhaps your LLMs, on how to actually engage with CMake in a healthy way, just to get you started again, all right? My background from where I'm coming from on this is at Bloomberg again. We have thousands of engineers writing CMake all the time. We have tens of thousands of projects. And we don't use a very special CMake style. There are some small differences between what I'm asking you to do and what we do internally, but it's more because we're ahead of you in some ways and not because we're doing anything that's particularly special or weird, all right? My focus is on developer experience. I really want to make sure every one of you is productive and working on the problems you're supposed to be working on, not fiddling with your build system or something, right? I want everything to be portable. I want your CMake to be as portable as the C++ code you've carefully crafted in those same repos. I want you to be able to turn to your colleagues next to you and they can see exactly what you're doing with your CMake configuration and not get confused about what's going on. And I definitely want your CMake to plug into all the rest of the rich ecosystem that is available so that you can really get the power out of your projects that you want. You want best-in-class CI. You want your IDE to just work. You want dependencies to just click in with the rest of the things you're working on, right? So to roadmap where we're going today, I'm going to walk through some resources with you, like I'm going to recommend for you to continue coming back to over and over as you grow even more in your CMake. I'm going to walk through how you command the CMake program itself. A lot of the power comes in just understanding how to do that. I'll talk through some principles you can use when thinking about the CMake you write for your own projects. And then I'll show you an actual example of all of this. It really helps, I think, to understand how things are going to work by seeing it in action and in a real project with real CI that is really being contributed to. And this is an open source project. As I go through my talk, watch out for this sparkly emoji here. That means it's something new that you probably haven't seen. It may not be brand new, but it may be something that someone's never shown you before and something I've, in my experience, have seen being underused in some way. Also watch out for these magnifying glass icons. That indicates a real piece of code, and to the best of my ability, on the exact line numbers of the exact files where I grabbed them from. This is a snippet of a README about a project that I'm going to use to demonstrate some of these principles to you. And it's the 2.2.1 release exactly, add that commit SHA in case you're curious. The project is part of the Beeman project. You might not be familiar with the Beeman project. It's only about 18 months old. Its main purpose isn't to advance CMake practices. In fact, its main purpose is to advance the standard C++ library by creating a collection of individually maintained but collectively owned C++ proposals with backing implementations that you can download, integrate in your projects, and so on. So its main purpose isn't making advancements in build systems. Its main purpose is so it wants to be as boring as possible, but as useful as possible in that effort, as far as CMake goes. So it makes actually a good demonstration for the rest of us that aren't trying to make waves with our ideas and build systems. The project, within that Beeman project, we're looking at the exemplar repo. That's its URL there on the slide. It is a C++ library. What it does is not interesting. It's just an example project. It could just as easily be a hello world. It's literally a project template. So if you check out that repo, there's a cookie cutter subdirectory that uses a Python utility called cookie cutter. You can look it up and what it does. It's got a pretty intuitive interface. But if you run the command cookie cutter against that directory, it'll ask you some questions. And when you're done, you have a full repo with whatever names you want out of it. And again, it's not trying to do anything special. It's trying to do just plain, vanilla, good, hardworking CMake. So on to some resources. I'm going to give you a lot of advice here, but it's not going to be complete. I'll reference different kinds of reference docs in CMake Upstream, but you're going to want more support than that, I think. So when you hit a snag, you want to get a little deeper, you want some advice, these are places I recommend. This is a QR code to a gist I have up available. You can go to that gist to get to the links. You can star them, you can send me messages at that up on GitHub to add more things or improve them or something. I recommend the CMake Discourse, hosted by Kitware. I recommend the Professional CMake book by Craig Scott, which is the most in-depth discussion of how to use CMake, both from a practical and from an expert perspective. There's a CMake channel on CppLink Slack, which is sponsored by the C++ Alliance. There's a lot of people like us hanging out there that can help answer your questions, including a lot of core CMake developers. I also, of course, if you have issues, questions, confusion even about the documentation, there are issues on the CMake Upstream. Again, actively maintained, I can vouch for that. I've had a lot less success in these two resources in particular. I feel like the CMake topic and Stack Overflow could kind of use some purging and refreshing. A lot of the answers are from maybe 10 years ago even. It'll work. CMake is fantastically backwards compatible, but you're gonna have a much better time if you check out the cool stuff that we've been seeing land in CMake in the last 3 to 5 years. Because of that, probably LLMs also give you kind of spotty advice. Probably because it saw that on Stack Overflow, and so it assumes that's what you want too. And I'm here to help maybe start correcting that record, get some of these advances incorporated into our collective knowledge here. So there's some resources. Let's dive into some more practicalities, right? How do we run CMake? This will be a review for a lot of you, because if you're here, you've probably used CMake at least once, right? This will be a bit of if you've never used CMake before, hopefully you can follow along well enough, but I'm not gonna discuss in depth all the ins and outs. But there's roughly, I'm gonna break it up into 5 basic stages that go into making a build happen. The provision stage, let's start there, is where you would set up your environment to just get set up your environment to prepare for the rest of the steps. You're gonna get your build machine going, so to speak, right? Anything that looks like going off your box to get something would, in my mind, fit in this step. That's this, including the source code for the repo you're about to build, exactly what version you were gonna build. Versions of your dependencies, maybe you need to get their source code. Maybe you need to install certain tools for your code generation to work. Anything that looks like you're going somewhere else or pitting a specific version of something to be successful, that's in the provisioning step. I really recommend you all look into package managing tools, at least try out the tutorials of the popular ones you might have heard of already, like Conan BC package, that sort of thing, or at least learn which packages are available in the distros that you might be using at the OS level. You have to be careful though, because the reason I recommend that is because there's a lot of complications in just setting yourself up for success later. You really need to make sure that when you're making these choices, they all fit together and they were built together in particular in a way that's compatible. I'll get into some pitfalls about that later, but it's easy to grab one flavor of one thing, another flavor of another thing, and they don't fit. And you get a bad build or something worse later on down the line. So it's important to be careful at this step about picking things that work together, hence the job of dependency management tools like package managers. Maybe you're a really big fan of monorepos. They serve the same purpose so that you have your head commit that all has a bunch of things that are all tested together. But often it's not as bad as all that. Again, if you're in a monorepo, just keep your head branch working. Maybe you have a container image that you like to develop against and you continually use that. Maybe you use Ubuntu and you just know which dev packages to install, or you learn how to do that. Or again, if you use like package managers, often you just go through the tutorial and it's a nice step along the way to get somewhere else, right? So with that out of the way, it's important to define that that was not part of the CMake step, but it's very important to be successful later. The next step is to go ahead and make a build directory. That's the basic CMake command. If you've done this before, or a tool has done it on your behalf if you've used CMake before. This is a form that maybe some of you aren't using though. In particular, this -B flag to define where your build directory is. I think like literally this morning, I was doing some kind of agentic development workflows, and it was changing directories around to try to run CMake in different directories. And I didn't need it to do that, and it actually kind of messed up the terminal state, because that's a stateful operation right now. Now, how many dots did I need to put in to go back to my source directory again, right? So this is really nice because it's more of a stateless operation. It's nice for, again, agents. They don't have to think about, wait, where was I again? Or like run ls or pwd again just to see what it was doing. It's nice for CI scripts because, again, they don't have to juggle all this information either. It's often you're going to add configurations at this point. Again, you want to front load a lot of these choices here at this step and not later and not in later steps. And so it's really common to add flags at this point. When someone says CMake variable, when they're talking about CMake, they're talking about these usually these dash capital D flags with a key equals value qualification on it, right? So in this case, this might be a flag to enable testing for this particular repo. And then there are other flags too. Read the CMake -- help docs. There's a bunch of really cool things that you might not even be aware of for debugging your workflows. In this case, I'm demonstrating -- fresh, which you might not be aware of. What it does is it actually blows away your configuration and reconfigures. Historically, people are actually deleting the whole directory and starting over again with stateful things that if you add a space, oops, I just deleted the whole directory, I didn't mean to, right? This eliminates those kinds of pitfalls. You're going to select a generator. CMake is, some people call it a meta build system, and in that it generates a different kind of build system to actually run your compiles and your links and your other steps. By default, newcomers aren't aware that by default you get a Unix make files base 1. That's because it's maximally compatible. They're the most kinds of systems will have a make file available. But at this point in the year 2025, you should really be picking a better one for what your workflow is. If you don't have a strong opinion, Ninja's fantastic. It's going to be faster and more featureful in a lot of ways. But if you're doing an IDE development, you're using one of the IDEs listed in the CMake -- help docs, look at those generators. They might have a much better IDE experience for your workflows. Something a lot of people aren't aware of is that you can actually select your generator with the CMake generator CMake variable, or also as an environment variable, importantly. So you can set that in your Docker file, your dot files, and that sort of thing, and avoid having to add --G flags every time you want to make a new build directory or something. You're kind of setting yourself up with a new default for that workflow, for that environment, for that shell session. All right? Also, if you haven't seen it, read the docs in the Ninja multi-config generator. It's really nice if you're trying to do like optimizing while still doing debugging in the same session and things like that. I don't have a ton of time to go into that, but it's really popular. You should look into it. It's really common to pick a quick question?
Yeah.
Okay.
Just a quick one.
Yeah.
You provide -G and
Yeah.
the environment variable. What
Yeah.
do you take?
If we get -G and the environment variable at the same time, the environment variable functions as literally like a new default. So the -G would override that. Make sense? And that's true of all the environment variables I'll be mentioning today. That's a good question. So the CMake build type is how you select maybe a flavor for your build. A lot of people don't know that by default, the flavor is like an unspecified kind of name, but it means compiler defaults. And actually a lot of package managers like that because it's maybe a lot closer to other build systems in different ways. They don't have to wonder like, what flags did CMake magically set behind the scenes on my behalf? I don't want that. So it's important as a maintainer of projects that you support all these options. So if someone wants to configure you with the debug settings, that you don't get in their way, but also if someone doesn't want to configure you with any build type, you also don't get in their way, okay? So by default, CMake supplies a few build types. Debug is a really good one for local development workflows if you don't have an opinion. Again, you could set that as an environment variable in your dot files, and then you don't have to think about it or type it every time. I do this in my dot files. I rarely set any of the things I just said. I just put them into my dot files, unless I have a specific need to do something unusual. One caveat is if you end up using that Ninja multi-config generator I mentioned, it doesn't use the same variable name build type because it supplies more than one build type. So there's a new variable name for that called configuration types plural. But same thing, also supports an environment variable. It's just a list instead of one value. So toolchain files. So to back up half a step, what is a toolchain? That's maybe something you haven't heard of before, at least not from me. It's a term of art in my circles for the compiler, the linker, the tools around those that help you really take those that source code and make it into executables and libraries and things like that. Maybe unsurprisingly, the CMake toolchain file is a file written in the CMake syntax to describe what a toolchain is and using the APIs that are documented in the CMake docs. They're really nice because it's really hard to get these right every project all over the place. So this is a nice reusable place to put those flags that are really important that you get the job done correctly. They're also used commonly by modern package managers to help do exactly that for exactly that purpose. The package manager might know you're doing a debug build or a sanitized build for this build. It'll tell you through the toolchain file so you don't have to add sanitizer support to each and every repo that's important to you. It's an ideal place for the ABI settings in particular, or anything that requires certain very sensitive compatibility modes. Again, supports an environment variable, so if you do have a toolchain file you want to use for that workflow, maybe a VC package provided one, just set that environment variable and move on, and you don't have to think about it for the rest of that session. Configure, again, sometimes you want to provide specific compiler flags. People like to do this a lot. It's generally not a great idea. Again, use the toolchain files for a lot of these things, but there are some that are harmless, like maybe you want to add a new warning. This is a flag that you may not be aware that GCC supports, which allows you to provide, you're basically asking it for a structured JSON file describing your warnings and errors, and there's a lot of nice tooling upsides to be able to get that kind of information. And this is how I do it. There's a few other ways to do it, but I like this way. You use the CMake_CXX flags, and you can add space delimited, that's a good caveat, a set of flags that you want to pass along to your compiler under the hood. The one reason this is interesting to do here is because at this point you probably know what compiler you're using, so you can use the flags that are specific to your compiler. If you push that information into your CMakeList.txt, now you have a bunch of if statements about, okay, if I'm on this compiler at this version and this day of the week, then I need to use the other form of the flag. This kind of keeps your project simpler just to know that this is here for you. All right, so at this point you have a build directory. It has a bunch of, let's say, Ninja build files in it, and you're ready to actually create some objects, some libraries, some tests, and so on. The next command for you is CMake-build. Again, you might not have used this before. Maybe the tutorial you've taken before says, change directory to the build directory, and then run make. That will work, assuming you use make as a generator. But do you really want to change your workflow depending on what your generator was? Wait, what was it set back when I ran it, when I set that environment variable yesterday? Well, this doesn't care. It'll run it for you. CMake knows which generator you used. It'll take care of it. The build flag takes as a parameter where the build rules are. So that's the binary directory I've been referring to in the previous steps. It runs by default a bunch of default targets. It's a little confusingly called all because it's not all the targets, but that's kind of a name carried over from make files back in the day. You can, if you don't want certain things to be built, like let's say you have a benchmark and you don't always benchmark in every workflow, but it's really important to support for CI workflows, you can use special flags, usually spelled exclude from all. If you search through the CMake docs, you'll find a lot of little hooks where you can do that, and I recommend checking those out. If you do want to build, let's say you wanted to build that benchmark target after all, you could actually just say -- target and then the name of that benchmark target. It'll build that even though it's not in the default list. It's also really useful if you have a very large project or otherwise your builds are slow and you don't want to build everything, you just want to build the one test you were planning on rerunning, right? You'll find your IDEs actually know about this and will do this for you under the hood. So again, it's important to know this is a hook here even if you don't plan on using it because someone else is going to want to use this. There are some built-in targets. I'm going to go through a few of them today. There's a few I'm not going to have time for today. I mentioned all. There's a clean target to clean up your artifacts and like maybe just do the recompile stuff. There's a test one, we'll get into that. There's an install one, we'll get into that. The one I'm not going to have time to get into is there's a new code gen one. That's something Bloomberg and Kitware have been teaming up with to better define that as a discrete step. It's really nice for when you want to pop open your code, you want to maybe do some analysis, or you just want their little red squiggly lines to go away in your IDE, but you definitely don't want to wait around for 2 hours for your link to finally finish, right? So this will just run, if you use the hooks that are supported, it'll just run the code generation, you'll have all the code, and then you can get on with whatever interactive development you were planning on doing. The API to look at the most, if you're interested in that, would be the add custom command API with the most recent versions of CMake, and it'll describe and link to other resources on how to get that to work. When you build, it's really common for newcomers or people running CI to want to see all the flags because maybe you're troubleshooting something or you really like to see like what the commands are. Wait, was that search path correct or was that pointing at the wrong directory? That kind of thing. There's a -- verbose flag. Historically, other workflows that you might have learned about CMake have other ways to provide verbosity that are maybe less intuitive and maybe harder to find. This is easy. It's the verbose flag. Just add it. You're good, right? So if it seems simple, that yeah, good, we did a good job. We got the API right again, right? If you don't want to type verbose over and over again, there is a CMake variable for that. You may not be aware of it. It's a little confusingly called CMake verbose makefiles, but it also works with Ninja, etc. It's basically saying, well, verbose for this build is on, right? So you just ran the build, everything's built, you have your tests built. Now you want to see if you have any like runtime bugs. So you're going to want to be able to test things. There's a few ways to do this. These are both valid. I really like the first form though. It's ctest --tester. And again, point out wherever your binary directory is. No need to change your directory. You have to be a little careful, but with how you design your tests, that you're not assuming a certain directory is the current directory when you run them. But there are CMake APIs for that if they're not, if you wanted something a little more sensitive to that. But what it does is it just runs your tests that are registered with the test target I referenced earlier. I'll show later how you mechanically make your test registered in that target, but this is how it works. Again, IDEs know about this. It knows about all the features in it. And IDEs tend to run exactly ctest when they're trying to test your code because there's so many nice features for it. You can set verbosity settings for output from your tests. You can filter, you can sort, you can run it a loop all night long if you want to. There's a really advanced ways to say tests that depend on other tests, so you can have a nice setup and tear down logic before and after certain steps. Again, Craig Scott's book, Professional CMake, and his blog have a lot of really nice resources on all the advanced testing workflows that CMake supports and like inherently already baked in for you. So again, you don't need to innovate on a lot of those features, it's already in there. So one thing that people stub their toe on a lot is maybe they jump into the repo, they run ctest, and then they get one of these. You get some like test name _ not built. Well, that's because CMake by default doesn't build your tests. Intuitively, you think they might. There's reasons historically and technically why it doesn't. Or maybe someday we can figure out maybe we can figure out a way to work on that a bit later. But you need to build your test first, and then your test will say, oh, there's the executable. Now I can actually run that test. Okay, so you've built your project, you've tested your project, you're ready to actually give it to someone else to be useful. Your library is ready to build against, your executable is ready to ship. So CMake provides that install target I briefly mentioned earlier for that purpose. Use it for packaging. It also is useful for just installing in general. It does extra preparation steps in the process of installing that makes it work in your production environment and not just in your build environment. The API I like the best for installing, and again, LLMs don't always use this one like I wish they would, is this one, CMake -- install, and you point at the binary directory. This parallels a lot of the earlier steps I was pointing out, and that's good. It's good design. It's more intuitive. The feature that people miss the most on this is the destdir feature, which is an environment variable for reasons involving Ninja. You can ask me or some of the CMake core engineers that are here about why that has to work that way, but it does. Destdir is an environment variable for where you want the installs to actually go. A lot of people try to shove that variable into something called the install prefix, which technically can work, but practically speaking, there's reasons that's more awkward, including for packaging and certain kinds of other workflows. So destdir is an environment, and again, it's an environment variable. If you know you're gonna throw it in this particular temp directory, set it in your local shell, moving on with your life, right? Prefix is where you would put, it's different. It's where it's supposed to be analogous to on a POSIX system, user or something like that. User or the root directory, one of those kinds of directories. You're looking for like the Linux file system hierarchy type locations usually. It depends on the OS, of course. The default is actually user local for the most part. Although sometimes you might want to put in a vendor-specific directory, something like an opt beamin could be appropriate if you're, say, you're doing a special install location for beamin projects. Most people are looking for destdir, though, not prefix. Quick question?
Yeah, so I don't understand. If you did this, where does it install in the system?
If you run it this way, it will install into put it here /opt/beamin, and then you'd have like a /include and then your header files or something like that.
And is it just for illustration, or there is a good reason why you would do both destdir?
Is there a good reason you would do both? Yes, because you might have different components you're installing. You might want to put them in different places, for example. Like you might have one package that has multiple libraries it ships, and you want to bundle them up in separate like tarballs or something. That's one use case. There's other ones. So you could have a different destdir, but maybe the same prefix across all of those. We don't have a ton of time for extra comments. If we can save the rest for If I'm not being clear, that's a great interruption, but hopefully I can get it through fast enough that we have time for a few questions at the end. So that's the basic workflow. It's not too bad, really. I mean, I'm going through it pretty fast, but I'm not, it's not too confusing, I hope. Hopefully it's somewhat review, but hey, that's a new form. I didn't see that before. I haven't been using it. So let's talk about some principles that go behind me showing you this. There's a reason I went through that first. So look at the slide number, right? I'm on slide 36. How much CMake code have you seen? How many lines? 0. That's about how many lines of CMake code you should be looking to write. CMake has some issues as like a language, and it has a lot of APIs again. It's really easy to implement your own build system in the CMake language. I've seen it happen so many times, and it really limits your ability to have an impact, to keep your projects easy to maintain, to interop with all the things. All that stuff I said at the top of the talk. So I discourage all this stuff. And a lot of these I will actually request changes in any PR I see with these flags. In a few cases, if you're just working around a bug, or maybe there's an edge case that you just need that CMake just doesn't support for you, you can talk me into it, but it needs a nice comment saying, hey, here's why I'm actually doing it the other way, and a technical justification, just like you would for if you had a go-to in your C++ code or something, right? So I discourage interop logic, as in like on Thursdays, my CMake needs to do this other weird thing, right? Like OS specific, like package manager specific, any of that sort of thing. Algorithms, for sure. Loops, for the most part. Variables, even, I generally discourage. I don't even do like my current library name and expand that later in the same file. It doesn't save me any bugs, frankly. CMake is stringly typed. It doesn't tell you that it doesn't know what the identifier is. It just expands that variable to nothing. Then you get a weird error. Conditionals, likewise. There's some tasteful use of if, but even then I keep it to a minimum if I can. So instead, describe your project. What are you building? How is that laid out in your source directory? What are the dependencies? Which targets, which executables, which libraries own which which headers, which source files. It's all factual. It's not something that's going to depend on where you're running it, who's running it, or when they're running it, all right? Hopefully you'll see that demonstrated later as I show you some examples. So day to day, what does your CMake life look like? It doesn't look like, oh man, I really need to implement coverage analysis in my CMakeList.txt. It looks like, oh, I'm just going to add another library. It's in this directory. It's got these source files. And I guess I need to pull in that one more dependency. Basically like that. It's listing things. That's why it's called CMakeLists, and not CMake algorithms that someone else has to maintain later and they break because I decided to port to Mac OS, right? Okay. So all the things I just described, also don't break those. I hinted at that earlier, but this is me emphasizing it. Someone wants to set CMake build type on your repo. Don't get in their way. You don't set CMake build type, that's not for you. If you read the CMake reference documentation, it says, don't set the CMake build type, that's not for you, all right? CMake CXX standard, I will have a slide on that. In particular, that is something I also discourage setting. And that is one that almost every time I see a template, a demonstration, or an agent recommending me CMakeLists.txt, it will set that for me, and I don't want that. It's wrong in the CMake tutorial according to, someone that's promised to fix that is saying it's wrong in the upstream CMake tutorial right now too. So maybe this is breaking news for everybody. Again, specifically in the test workflow, I like to see everyone have a test target that is defined. I shouldn't have to guess whether I should or shouldn't run the test target on your repo. I should just be able to run it. So you have 0 out of 0 tests passing. Fine, at least I know that you have 0 tests that are working in my current workflow. I don't have to wonder, did they put it in a weird target? Do I have to go read a bunch of CMake code just to figure out how to test this thing, right? You don't want your project to be too special. You want it to plug in nicely with the IDEs that already know about the test target and things like that, right? So if you do want to have, sometimes you do have a special test. It's not always on. I mentioned benchmarks, or maybe you have a really hairy integration test or a fuzzer that you don't always have turned on. Fine. But you could have an option, like this is an example of an option that the Beeman project uses to say, sometimes I have something on and sometimes it's off. And then can use that as a conditional later and add that part of your project in or out, depending on whether the user wants it or not, right? So this is my slide on CMake CXX standard. The Beeman project that I've mentioned already has as a standard. It's called the Beeman standard. This is a QR code to that document if you're interested. Inside that, we have something called passive projects. That's the term we came up for this idiom, right? The idea that you should be receiving the flags that the person building you wants to use in your build. The C++ standard, surprisingly to a lot of people, is very sensitive setting to set at any large scale. The scale of 2 to 3 repos that you personally maintain, not a big deal. But the second you start working with other repos, especially popular repos that have a lot of weird edge cases they need to support, things get kind of weird pretty fast. And the reason it gets weird that might be surprising to you is that while the C++ standard library goes to great lengths to make sure that you have compatibility across different kinds of standard settings between different files and different libraries, we can't expect the same kind of rigor in every single project out there in the ecosystem. And in fact, some are designed to basically not be that rigorous. Anything that provides a backport in particular of a future C++ library feature, including the Beeman project, is literally ABI incompatible with itself depending on whether you have that flag on or off. ABI incompatibility means ill-formed code that requires no diagnostic. It could fail at any step of any of the things I just said today, or even later in production with data corruption issues. This is a very important thing to take seriously. So the reason we don't set it per project is how do you ensure that every CMake project that you linked against all had that set statement exactly the same and compatible? The easiest way is nobody sets it, we put it in the toolchain file, or we set in the CMake CXX flags, moving on with their lives. And that's what my recommendation is. If you're worried that someone's going to get it wrong, or you're worried that they need a better help me if they aren't setting it at all or something, it's okay to fail fast. It's okay to say, hey, I can tell, ideally in your C++ syntax, hey, I can tell you're not actually setting the C++ standard ranges that I support. I'm going to stop now and give you a nice error message. That's great. You should do that. So to summarize with a visual aid, CMake does a lot of things. You can implement all sorts of things, including ray tracers famously in the CMake language. You could do all sorts of stuff. It's best at the stuff I just walked through, though. You know, accepting the provisioning step, because I specifically said that sets you up for the CMake workflow. You configure something, you build something, you test something, you install something. Maybe some code generation in the middle there. That's fine, all right? So let's look at some actual code snippets. We're going to go into the Beeman exemplar project I talked about. Before we get into that too much, it's important to realize that there's names in the next portion. So a lot of what we're doing here is trying to make sure that when we create something, when we export something, when we depend on something, everyone's using the names that match each other, so everything clicks together nicely like Lego bricks. Make sense? So the Beeman project likes to be consistent about its naming, so it's got specific naming conventions. Almost always it's Beeman as like a first name, and then another project name as the second name, and they're joined together with some sort of delimiter. And like basically everything that Beeman picks as a name includes that full qualification, so it can be specific about being exactly that thing you wanted, and being disambiguated from anything else in the whole repo, the whole world that might be named exemplar or something like that. Especially if you have libraries named like util or core or database, like you really want to make sure you're qualifying things so nobody's building the wrong thing at the wrong time, right? This happens a lot with test targets in particular. People will name their targets like test, or actually if you name it test, you'll get errors, but anything like unit test or integration test, you might collide with other people in surprising ways. So those are like provisioning step things, like what you name your package. We like, again, Beeman exemplar with some kind of delimiter. These are the ones you might see in your CMakeLists or similar technologies for like how you might qualify and find Beeman. You know, Beeman dot exemplar is our favorite, but sometimes it has to be a double colon for that particular technology doesn't play nice with dots or something like that, right? And then even in your C++ code, again, use naming conventions. Use your namespaces that follow the same conventions. That's not a strict requirement, but it's nice for your users. And again, you want to be specific. It's going to really stink if your library named database ends up colliding with some very important open source or standard thing, also called database at some point. You're going to be in a real tough spot. So try to qualify things as much as you can. So let's look at actual code. So we're going to start on your top level CMakeList.txt. This is what sets your whole project up. The first line, the first substantial line in your project. You can have your SPDX identifiers in your top of your file, description of what you're doing or something. But the first real line, CMake minimum required, version, and what compatibility version for your project are using. What did that mean, right? The one guy that works on CMake knows. What it actually is, maybe surprising to you, is a compatibility mode. It's kind of a feature flag. And when you set that really old, what you're saying is, I want to be bug compatible forever and feature compatible, i.e. using old features, of CMake, let's say 2.8.11. I don't think any of you really want that, right? You just want to say, don't care too much and just work, right? The way you spelled it is actually keep it bumped. The reason you keep it bumped to as new as you can is because you'll see deprecation notices, you'll get these new features enabled, and other kinds of niceties, performance optimizations in some cases, by keeping that higher, okay? So what do you set it to? Well, if you're on a simple, basically just only work on your one dev box or something, run CMake --version, take the major minor version, paste it in there. It's fine. If you support a lot of platforms, okay, go to every platform, do that and set it there. We did a quick survey of a lot of popular open source available platforms in the Beeman project. We found out 325 was actually supported across the board. So it's maybe a lot newer than you might expect. This is only about 2 years and 3 months old or something like that. The next line that's interesting is the project line. There's a lot of options you can provide. This is just showing that you can. They're not, if you want them, you can set them. If you don't want them, you don't have to set a lot of them. But have the project line next. That's the important thing to take from this slide. I mentioned those toolchain files. This is the line of code that loads those toolchain files. If you've ever gotten a confusing error about CMake script mode and something not being defined, or just a variable that's supposed to be expanded into like the OS name or something just was an empty string, it's probably because you did it before this line, or you just didn't have this line. I've seen people do this because they pointed at a subdirectory of their project instead of the top level, for example, which would not have necessarily a project statement, okay? It confuses CMake, it confuses you consequently, all right? Again, this is how you implement my recommendation that you always have a test target. There's different ways to spell it. The Beeman project includes the ctest CMake module. That's about all you need to know for the purposes of this talk, but it does some other things too. You can go read the docs. They're more intermediate, advanced C-test workflows. If you're interested in that, Daniel Pfeiffer has a talk at C++ Now 2025 talking a lot about C-test and all the cool things it can do. This describes more of your project structure. Again, it's declaring, hey, I have more CMake in these other directories, and it literally goes and looks for a CMakeLists.txt file in that directory and just pulls it in as a procedural step. So we're adding the subdirectory that includes the Beeman library itself. This is demonstrating how to use that option we talked about earlier. Sometimes we want to build the examples, sometimes we don't. So you can put a conditional, wrap it around your add subdirectory, and everybody wins. Is this confusing? Everyone gets this. So let's go into that subdirectory with the library. Note the code snippets were in a different directory now, a different file. So we're going to declare a library. You can do it in a quick short statement. That's the line number 3 here. You just need to say add library and the name of the library. No fuss, right? The second line is adding adding more of an external API version of that same library. There's a few reasons for that, but just to get the mechanics out of the way, it's an alias library and it's pointing out the thing you just declared, all right? So alias libraries, you should always use a double colon name. So I recommend if you have a delimiter, just replace that with the double colon like we did here. How would you use those? Well, inside the same directory, or when you're manipulating exactly that target, use the first name. That's like your special private name, right? That's your personal super top secret name that witches can do voodoo curses on you with if they knew what it was, right? So don't tell anybody else what that name was. That's for you. Beeman : exemplar is your more public name. Right? So other targets in the same repo, definitely anything outside of your repo, they're going to use that name. Does that make sense? There's a few reasons for that. The one that's best for you all to understand is if you have something in a target link libraries command listed as a dependency and it's spelled with 2 colons, CMake does extra checking for you because it can tell that it's supposed to be one of these logical target names. It will tell you, hey, by the way, you never defined that thing, so I'm just going to stop and you need to go figure out what you spelled wrong or what you forgot to import. And you want that, because if you don't get that behavior, what CMake does is, maybe that's a library installed somewhere. I'm just going to put it on the link line and see what happens. And we'll see what happens. So you don't want that. That's bad, right? That's late breaking errors. You don't want that. So use the double colon. The other bad problem with it just slapping something in your link line is, what about the header files? Is it pointing at those header files, or are they the right version of those header files? I don't know, right? So this is why you always want to use these alias libraries, especially in these situations. Target sources is how you would associate different kinds of source code with those libraries or executables. By the way, keep saying target. In CMake language, target is just a library or an executable, or something that's supposed to behave like a library or executable. Anyway, so you can associate source code. There's not much to talk about here. It just does what you'd think. The private keyword is the first time we've seen something like that, I believe, on these slides. When you use private, just say this is something specific to me that nobody else needs to know about. So in this case, the library is going to build the code, incorporate it into the library, and everyone else doesn't need to know about that CPP file. They can just link against the library and be fine, right? Here's another invocation of target sources. This is something you're probably not doing yet. It's a little longer. I see some smirks in the back row. But it is better because it is longer, because it actually gives you something really nice. So the form is, the first word is, again, the library name. And these are interfaces. These are your header files. So it's a public thing. People need to know about your header files so they can include them, right? We're saying they're headers by saying file set headers. These are headers I'm going to tell you about CMake. They are in these base directories. You can have several. Most of the time, you're going to have just one or two, unless you have a really complicated project structure. In this case, we have a separate include and source directory, so we're going to go up a few directories. It's over there. That's where the include files are. That's where headers are. And then we're just going to list those files. CMake can tell the difference between the names of the files and the directories they're in, and it knows that when you install them, you're going to install that last little bit. Beam exemplar identity.hpp, that's the thing I'm installing. That's relative path. And that preserves that include path that you defined earlier for your users to use. Does that make sense? If we didn't have base stores, it might just install identity.hpp, and then you roll the dice on who else has an identity.hpp or a config.h in the whole entire world, right? There could be a lot. So this is a new feature. Again, Kitware, Bloomberg collaborated on this sort of thing in the last 3 to 5 years. It's really nice. It is the future of how we're going to support a lot of nice features as far as CMake goes going forward. It's going to really help you out. For the record, if you've used CMake before, I use target include directories fairly rarely at this point. I just do this. Target include directories is kind of an unstructured way to just slap things into your built compile commands, and you kind of roll the dice again on was that a header behind the search path, and what version of what library did I get when that happened, all right? Sometimes I'm working on a library that is already installed on the system, and because the -i was wrong, I got the old version of those headers, even though I'm trying to edit the code in my current directory, and I'm wondering why is this not working? One of those bugs. Raise your hand if you had one of those bugs before. Yeah, it's that. So this tells CMake, please help me make sure that doesn't happen, please, right? It has other nice features though. I talked about it. It's just a nice model. It also helps, CMake knows how to install given that. It knows, the headers go with the library, I'll go ahead and install those too. It fixes your include directories. I don't use those anymore. It can also validate your headers. There's a feature that is fairly rarely understood or used, but the Beeman project uses it because I told them to use it. It lets you actually verify that the headers compile on their own. There's actually a lot of bugs, maybe you all have seen this before, where maybe a header doesn't even work at all. It is not valid C++ syntax. There's just a straight up bug in there. But nobody has ever included that header at all in the entire evaluation process of that pull request. So I just slipped through, and then I went to your clients, and they say, what gives? Am I doing this wrong? And they're gonna be like, oops, yeah, I didn't test my files. So what this does is prevent that by CMake knows that you have headers. It knows, because it knows about your library, how to compile those headers. So it just generates targets to build those headers. It's as simple as that. It also puts them into your compile commands JSON file. I don't have time to explain what that is, but that's a really nice interface for static analysis tools, IDEs, and some other things to also know about your source code. Quick question?
Yeah, if you set that property, do you pay for the verification all the time? Or just...
If you set that property, it creates okay, that's a good question. So the question was, you're basically asking, does this increase compile times because you're parsing those headers? By default, the all verify interface header sets is not as part of the default target set, but you can invoke it directly using the --target command that I mentioned earlier. That being said, it is in your compile commands.json, so you might, if you run clang tidy against that build directory, it'll be picking up some more things to analyze, but that's kind of the point, isn't it? Right? Okay. Does that make sense to everybody? Or good enough? Okay, you can ask me later if not. So at this step, we actually have defined our library. That's all you need to do. There weren't that many steps, right? We just defined it, hey, that's the exemplar library, all the code that's in it. It doesn't have any dependencies, so we didn't have a step for that. What we're gonna do now is install it. This is how we do it in the Beeman project. We call find package to pull in some CMake code that we're gonna use in a second. The next line is to use that CMake code. So find package Beeman install library defines the Beeman install library function, and then we call it. And that's where we put a lot of the complexity of our install process into some reusable code that we can use across several projects. I really recommend you all think about this, especially for your organizations where you have project structure conventions, you have installation expectations, that sort of thing. Use modules. I have a talk about this back in 2021, where I spent a whole hour here at CppCon talking about CMake modules, how you can ship them, how great they are, how they'll make your code generation amazing. Check it out. In particular, what the purpose is, those names I talked about earlier, is just making sure that those all line up for your consumers. That when they call find package, they can spell it beeman.exemplar and it gets resolved. That sort of detail. That when they call pound include, they can spell it beeman exemplar identity.hpp, and they don't have to mess with target include directories to make up for your mistakes, right? I don't have time, the actual implementation of that is a little slideware hostile. So you'll forgive me by summarizing it with a few shorter, simpler versions. These are the simplest possible ways you can install a library. You're probably going to want more features, but you'll know what the APIs are. You can read the reference docs. You can adjust from there. If you get stuck, again, I just gave you some resources to go say, hey, what do I do if I want to ship a shared library with a different SO name or something like that, right? So this is how you install a library or an executable. This is a library in particular. So we're installing targets, right? And we're installing the library target we defined. We're exporting, that's a correlation ID for later. It's going to be useful later when we try to generate the find package support for this project. So it's just saying, I'm making a correlation ID called Beeman exemplar. I'm going to define a find package support for this later. Just so you know, this is targets going in that find package. And then we're saying file set headers. Yeah, take the headers along with it. I'd rather have headers than not. Right, I said all that. This is the quickest way to possibly have a config find package beeman.exemplar work. Export is that same collation ID, right? So it's the next line, so it's hopefully not too confusing. You can give it a different name if you want to. You could call it export name or something. It's putting it in a destination. That's a magic path for you all, but if you read the find package docs, it gives you 75 different places you could put a CMake file, and this is one of the easiest ones to put on a slide. The CMake install libdir is a special variable. It's defined by that include on the first line there. That include defines that variable so you can use it. Yeah, again, this is why I use Beeman install library, because it's like, does everyone in the whole room need to learn this? Maybe not. The namespace is interesting. This is how we support the Beeman : exemplar interface for your consumers, that they can add that as a dependency for their executables or libraries. It's the Beeman : and Beeman : exemplar when they want to depend on you. So it's important to get that right and spelled correctly. The next line is the file. That's the base name of a file that you're installing. There's a few ways to spell this. Again, find package docs describe all the possible ways you can spell it. This is a nice one. I like the kebab case, -config.cmake. Find package knows to look for this. When someone calls find package, the last line you may not be able to use yet. In fact, you almost certainly aren't, because it's an experimental feature, but possibly even by the time this comes out on YouTube, it's something you can use in the newest versions of CMake. This is really cool. It's brand new. That's how new it is. It's still experimental, but what it does is to make sure that your transitive dependencies are well declared for your consumers. So if you depend on FMT, they can transitively depend on FMT, and you don't have to do any extra hairy CMake stuff to make that work. This is more for the existing and advanced CMake users in the crowd. The rest of you be glad that when you get it, this will be here for you when you get to that point. So all this is just to make find package Beeman exemplar work. Again, we're iterating on this as a community. We're moving to more JSON-based installation stuff that's going to be a lot more intuitive. But this is the current state of things. So I talked about Beeman : matching. So awkwardly, if we stop there, we would be exporting something called Beeman : Beeman.exemplar. That's not what you want to spell, is it? Now, if you're the FMT repo, it would be spelled, your library would be named libfmt.a on Linux, and the target name would be fmt::fmt. You could have stopped right there. But in the case of Beam Exemplar, it's an awkward name. So the way to fix it is with this, is it's called a target property. It's literally just setting like a variable on the target, and it's saying, yeah, I have a different name. You could drop the second beam and just call it exemplar after the : : And that's it. Okay, that was weird. That was the hairiest part. It was still only 3 statements, right? And you have to read some docs for some of those. So Vito's here in the room right now. He has a fantastic talk I really enjoyed at C++ Now 2025. I don't believe it's on YouTube yet. It's up? It just got posted like this week or something. Great, so you can go find it. It goes into a lot more advanced detail on those last 3 slides. So if you're scratching your head a little bit, you can watch his video. He'll get into that a little bit more. If not, you can harass him in the channels I mentioned earlier. He'll be obligated to correct his mistakes. So we haven't talked about actually running your test yet, right? So let's talk about how to wire that up. So we're changing directories. We're in the test subdirectory now, right? Wherever you want your test source code. It could be the same directory, but in this case it isn't. We have a dependency in this case. The project uses Google Test. So this is us using someone else's exported API. Gtest has some .cmake file and some magic lookup directory that CMake supports, and so we call this and it works. Use required, by the way. That way you get a nice error message if your dependency is not there. The only time you don't want to use a required is when you're doing special case logic about what day on the week do you want to use Gtest versus catch2, and you don't want to do that. So you want the nice error message. It defines, if you read the Google Test docs, it defines the Gtest : Gtest interface for you to depend on, just to be clear, because that's going to be important in the next slide. So we're adding an executable. Again, I picked a really unique name. That's a long name for a test, isn't it? You probably just named it unit test, didn't you? But again, the longer it is, the less likely you are to collide with other things, like other projects you might want to add, like combine into one big super build or something like that. So it parallels a lot with what we just did. So I won't belabor this slide too much, but we have an add executable command to make an executable. We're going to associate source code with it. And then we're going to declare our dependencies. This is the only place in the whole Beamer project where we do, so it's worth going over. Target link libraries is basically add dependencies, right? So Beam and exemplar test identity depends on Google Test. It also tests Beam and exemplar, so it's going to depend on that as well. Notice the : because the test is in a different subdirectory. It's like kind of an external consumer to the actual library. So it's using Beam and : exemplar as its dependency name. And oh, by the way, if you do have header files, you can still use file set headers at this step if you want to, all right? We don't, so we didn't. So all that does at this point is declare an executable, though. As far as CMake knows, that's your production code, right? How does CMake know it's a test? There's different APIs for that. If you're using Google Test or catch2, there are nice APIs for those systems that teach CMake about the specific test cases for those test suites that you just built. And it wires up nicely the filtering, the sorting, the randomization, the looping, and all those sorts of things that you might want to use in your development environments. Your IDE knows about these. So like if you have a nice IDE setup where you can click a little play button next to your Google test case, and it runs just that one test, that's because somebody did something like this or used an API like this. So if you have something specific, it's probably in your best interest to use it. That being said, there are some edge cases where you might not want to do that, especially if your test is slow or something like that. There's a more basic API for just saying, I just have a test, you're going to run this executable, no frills. This is what it looks like. The command is literally a shell out command, so you could add flags at the end of this. If you look up, again, CMake documentation, you can set properties on the test. I mentioned a lot about dependency declarations, but you can also set environment variables, current working directories, and things like that. All right, so that was all of it. I'm done. So optimize for simple declarative CMakeList.txt. I talked a lot, but there weren't that's because I was really explaining all those statements. There weren't that many, there were 15 or so. And you might be surprised at how far you can get with that little amount of code. You only want a handful of statements, declarative statements. If you find yourself doing something interesting or unique in that project, you probably want to take a pause. If you don't want to do it across 12 projects, across all the open source projects you're interested in, do it on behalf of your teammates, it's probably too much work for that project. You should take a step back, ask somebody, is there a simpler way to do this? Because usually there is. Use the features of the CMake command more. and the CMake language yet less, right? We don't want to write a new build system in CMake. We want to just use CMake, the build system, right? Defer to tools with more context. That could be your CMake presets. If you're tired of boilerplate, if really all you're trying to look for is ergonomics, use some of these features designed to help with your ergonomics. Like have a CI system that is more robust, understands CMake, knows how to run these commands like I described and get you the right answers. It is also going to know more about like what OS you're targeting and make sure those flags are plumbed down that are compatible with your compiler, for example. I've seen people write top-level make files in their CMake projects that work actually really well. It just says CMake --build as like a build target or something. Just make sure that you keep the project structure details to your CMake and keep your workflow details to the make file. And then you have a nice division and there's not a lot of confusion about what goes where. Package managers, again, good place to put a lot of context. Am I doing a thread sanitizer build? Do I need all my dependencies built with thread sanitizer? How does that work? Well, that's what they're for. That's what your package manager does. And that's the end of my talk. I appreciate you listening. We have a tiny bit of, I could probably have time for like 1 or 2 questions if anyone has anything they want to ask. Thank you. All right. A lot of questions. We'll have to do some in the hallway too. Yeah, go ahead.
Thanks for the talk. Just real quickly on the CMake CXX standard. If you're not recommending setting that, does that mean you also tend to avoid using target compile features and setting it that way?
Yeah, exactly. That's a similar issue where I tried all the vacations I could think of those other features, and all of them tried to default your C++ standard to try to be helpful. And yeah, Vito says you can use them privately. I guess he means behind locked doors.
Don't use it on libraries.
Don't use it. Okay, if you use it on the executables and your libraries are using it the same way, you can be fine. If that's not true or you're not sure it's true, then you're probably better off using it in a toolchain file or using it as a command line flag like -d CMake CXX standard or something like that.
Okay.
That makes sense?
Sounds good. And then do you recommend using like project name for target names or being explicit?
I don't like using project name because it's kind of stateful, like what directory you're in, and it can change if somebody like adds a project. If someone adds a project command in a completely different directory, your build just got weird really fast. So I just find that it's not that big a deal to keep pasting the name over and over. And again, if you spell project name wrong or left off the C right there in the middle somewhere, you're getting what? So like, what is it saving you really at the end of the day? You still have to make sure you don't get any typos in any characters at any time you're using it. So that's my logic. I've seen people use it. I've seen them use it successfully. I just find it makes my code harder to read with more curly braces and doesn't really prevent any bugs for me. Does that make sense?
Yep.
Okay.
Thanks.
Hi.
Hi, thanks for the talk. That was loud, sorry. So just wanted to know your opinion on maybe running static analysis tools via add custom command and creating targets for them that you depend on, say, an all. Just curious, like clang tidy, for example. I've seen this a few times.
Yeah, okay. I had slides in this in my version of this I gave at C++ Now because I had another half an hour. There are 2 ways to run static analysis baked into CMake. The one that I kind of mentioned was compile commands.json. That's probably the most popular way to do it. It's also how ClangD and other kinds of tools use it. And they can run like static analysis as like a sidecar onto your build without complicating anything you need to maintain or replicate across a bunch of projects.
So not creating a CMake target for that.
I don't find I need it. The other thing that you can do is there's a CMake CXX clang tidy variable you can set, and you give it the path to clang tidy, for example. There's also CppCheck and maybe something else. Include what you use has one too. CppLint has one. And we could add more if just go to the issues and ask. And what that does is it adds targets parallel to your build targets to do exactly what you say. So you don't even have to do anything. Probably what most people want is just that. When I build, I want to also run static analysis and give me all those at the same time. Literally the day I was doing that when I was doing some C++ development. And that's what I recommend, because then, again, no complexity in your project structure. Your IDE could do it if it wanted to. Your CI system could do it if it wanted to. And like everybody wins, I think. Does that make sense?
Yep,
Yeah.
thank you.
All right.
Bret, thanks for the talk.
Yeah.
I have 2 questions. One about how to set CMake install prefix. So right now I have like 3 ways of doing that.
Yeah.
Minus the CMake install prefix, then with the prefix option of the CMake, and then you can do it with the presets. Any recommended best practice way?
Okay, well, the presets, The presets are kind of like shortcuts for the other things. I think under the hood, all the preset features boil down to one of the other two that you're talking about. So I'll focus on those. There are some situations where you really need to know at configure time what the prefix is to do certain things. There are other ways to provide that information, like having a project-specific CMake variable that could be effective. But I find, especially when I'm using other people's code, sometimes they really, really expect you to have your prefix defined before they configure. Do what you got to do to get the build to work at that point. But I find in my projects, I don't need it. And then, in fact, it's kind of nice that if I wanted to install for one package manager, I wanted to install onto user, and another package manager, I wanted to install onto opt beamin, and I don't have to do a whole other build to make that happen. That's really nice. It saves some compute and that kind of stuff. So I like the form I showed for that reason, but the other one works. It just, it's a little more brittle in certain ways.
Okay. The other one, maybe a bit specific. So with ctest, when you build your project and it has dependencies, works well on Linux because it has rpath. In Windows, it fails with a cryptic error because it cannot find dependencies anymore in the build directory because dependencies are elsewhere. Any recommendation?
I'm not sure if all the workflow. That sounds like a good hallway question, though.
Okay.
We'll talk about that in a minute. Okay, last question. We're a little over time, but maybe they'll forgive us.
So I like the idea of having a very declarative CMake, but when I see add executable, target sources, target link libraries, install, it doesn't feel that declarative. Do you think we need better primitives that are more expressive and simpler to use for the 99% of users that would allow us to better teach CMake to users?
I think as long-term goals, I share that. I believe the core CMake engineers do as well. We have a lot of how do we get there from here problems, though. And the point of this talk was to say, what can you do right now? And assuming you can get a relatively recent CMake version, as in like last 2 to 3 years or something. I agree with that. We have a lot of success in our organization for those situations where you have more opinionated project structure using CMake modules to know about that project structure. Like if you always have a subdir of the source dir that always matches the target names and the project names and all that sort of stuff, well, you don't need all the boilerplate. Just say I'm using project structure X and then walk the source tree and declare all the targets for me. We have projects, we do nothing but have a schema for our middleware projects. You just put a schema file in the repo, and that's it. There's one CMake command you call, and it does all the rest for you. So I think we already have a lot of the tools per organization for that. Now, we don't have a standard C++ project structure. Maybe that some of us can get together and make a popular one, at least, if not a standard one. That might save a lot of headaches. And maybe beam-in project could be one of those things, like driving those kinds of consolidations, if that makes sense. Ultimately, I would like something like a cxx.toml, where you just say, I have a library and it's got these dependencies and these source files, or just it's in the normal project structure, figure it out. We just don't have that right now. It would also be nice and relatively portable across potential build systems, or maybe a CMake 5.0 someday or something, right? But yeah, so for now, I'm targeting projects I can ship in the 1 to 11 month range, and then seeing what I can do from the next annual cycle every year. And so far, we've been making some good gains. Point of this talk was to show, like, hey, where are we right now, kind of. All right, so let's keep talking in the hallway. This is how open source magic happens, is people saying, shouldn't we? And a lot of people say, yeah, but do you want to make the pull request, All right. All right, well, thank you, everybody. I appreciate it.